In telecommunication, information theory, and coding theory, forward error correction or channel coding is a technique used for controlling errors in data transmission over unreliable or noisy communication channels. The central idea is the sender encodes the message in a redundant way by using an error-correcting code. The American mathematician Richard Hamming pioneered this field in the 1940s and invented the first error-correcting code in 1950. The Hamming code. The redundancy allows the receiver to detect a limited number of errors that may occur anywhere in the message, and often to correct these errors without retransmission. FEC gives the receiver the ability to correct errors without needing a reverse channel to request retransmission of data, but at the cost of a fixed, higher forward channel bandwidth. FEC is therefore applied in situations where retransmissions are costly or impossible, such as one-way communication links and when transmitting to multiple receivers in multicast. FEC information is usually added to mass storage devices to enable recovery of corrupted data, and is widely used in modems. FEC processing in a receiver may be applied to a digital bit stream or in the demodulation of a digitally modulated carrier. For the latter, FEC is an integral part of the initial analog-to-digital conversion in the receiver. The Viterbi decoder implements a soft decision algorithm to demodulate digital data from an analog signal corrupted by noise. Many FEC coders can also generate a bit error rate signal which can be used as feedback to fine-tune the analog receiving electronics. The noisy channel coding theorem establishes bounds on the theoretical maximum information transfer rate of a channel with some given noise level. Some advanced FEC systems came very close to the theoretical maximum. The maximum fractions of errors or of missing bits that can be corrected is determined by the design of the FEC code, so different forward error correcting codes are suitable for different conditions. How it works. FEC is accomplished by adding redundancy to the transmitted information using an algorithm. A redundant bit may be a complex function of many original information bits. The original information may or may not appear literally in the encoded output. Codes that include the unmodified input in the output are systematic, while those that do not are non-systematic. A simplistic example of FEC is to transmit each data bit 3 times, which is known as a repetition code. Through a noisy channel, a receiver might see 8 versions of the output. See table below. This allows an error in any one of the 3 samples to be corrected by majority vote, or democratic voting. The correcting ability of this FEC is up to 1 bit of triplet in error, or up to 2 bits of triplet omitted. Though simple to implement and widely used, this triple modular redundancy is a relatively inefficient FEC. Better FEC codes typically examine the last several dozen, or even the last several hundred, previously received bits to determine how to decode the current small handful of bits, averaging noise to reduce errors. FEC could be said to work by averaging noise, since each data bit affects many transmitted symbols. The corruption of some symbols by noise usually allows the original user data to be extracted from the other, uncorrupted received symbols that also depend on the same user data. Because of this risk pooling effect, digital communication systems that use FEC tend to work well above a certain minimum signal-to-noise ratio and not at all below it. This all-or-nothing tendency, the cliff effect, becomes more pronounced as stronger codes are used that more closely approach the theoretical Shannon limit. Interleaving FEC-coded data can reduce the all-or-nothing properties of transmitted FEC codes when the channel errors tend to occur in bursts. However, this method has limits. It is best used on narrowband data. Most telecommunication systems use a fixed channel code designed to tolerate the expected worst-case bit error rate, and then fail to work at all if the bit error rate is ever worse. However, some systems adapt to the given channel error conditions. Some instances of hybrid automatic repeat requests use a fixed FEC method as long as the FEC can handle the error rate, then switch to ARQ when the error rate gets too high. Adaptive modulation encoding uses a variety of FEC rates, adding more error correction bits per packet when there are higher error rates in the channel, or taking them out when they are not needed. Types of FEC. The two main categories of FEC codes are block codes and convolutional codes. Block codes work on fixed-size blocks of bits or symbols of predetermined size. Practical block codes can generally be Howard decoded in polynomial time to their block length. Convolutional codes work on bit or symbol streams of arbitrary length. They are most often soft decoded with the Viterbi algorithm, though other algorithms are sometimes used. Viterbi decoding allows asymptotically optimal decoding efficiency with increasing constraint length of the convolutional code, but at the expense of exponentially increasing complexity. A convolutional code that is terminated is also a block code, in that it encodes a block of input data, but the block size of a convolutional code is generally arbitrary, while block codes have a fixed size dictated by their algebraic characteristics. Types of termination for convolutional codes include tail biting and bit flushing. There are many types of block codes, but among the classical ones the most notable is Reed-Solomon coding because of its widespread use on the compact disc, the DVD, and in hard disk drives. Other examples of classical block codes include LDPC, multidimensional parity, and Hamming codes. Hamming ECC is commonly used to correct NAND flash memory errors. This provides single-bit error correction and two-bit error detection. Hamming codes are only suitable for more reliable single-level cell NAND. Denser multi-level cell NAND requires stronger multi-bit correcting ECC such as BCH or Reed-Solomon. NOR flash typically does not use any error correction. Classical block codes are usually decoded using hard decision algorithms, which means that for every input and output signal a hard decision is made whether it corresponds to a 1 or a 0 bit. In contrast, convolutional codes are typically decoded using soft decision algorithms like the Viterbi, MAP or BCJR algorithms, which process analog signals, and which allow for much higher error correction performance than hard decision decoding. Nearly all classical block codes apply the algebraic properties of finite fields. Hence classical block codes are often referred to as algebraic codes. In contrast to classical block codes that often specify an error detecting or error correcting ability, many modern block codes such as LDPC codes lack such guarantees. Instead, modern codes are evaluated in terms of their bit error rates. Most forward error correction correct only bit flips, but not bit insertions or bit deletions. In this setting, the Hamming distance is the appropriate way to measure the bit error rate. A few forward error correction codes are designed to correct bit insertions and bit deletions, such as marker codes and watermark codes. The Levenshtein distance is a more appropriate way to measure the bit error rate when using such codes. Concatenated FEC codes for improved performance. Classical block codes and convolutional codes are frequently combined in concatenated coding schemes in which a short constraint length, Viterbi decoded convolutional code does most of the work, and a block code with larger symbol size and block length mops up any errors made by the convolutional decoder. Single-pass decoding with this family of error correction codes can yield very low error rates, but for long-range transmission conditions iterative decoding is recommended. Concatenated codes have been standard practice in satellite and deep space communications since Voyager 2 first used the technique in its 1986 encounter with Uranus. The Galileo craft used iterative concatenated codes to compensate for the very high error rate conditions caused by having a failed antenna. Low-density parity check. Low-density parity check codes are a class of recently rediscovered highly efficient linear block codes made from many single parity check codes. They can provide performance very close to the channel capacity using an iterated soft decision decoding approach, at linear time complexity in terms of their block length. Practical implementations rely heavily on decoding the constituent SPC codes in parallel. LDPC codes were first introduced by Robert G. Gallagher in his PhD thesis in 1960. But due to the computational effort in implementing encoder and decoder and the introduction of Reed-Solomon codes, they were mostly ignored until recently. LDPC codes are now used in many recent high-speed communication standards, such as DVB-S2, WiMAX, high-speed wireless LAN, 10G-based Ethernet and G.HN/G.9960. Other LDPC codes are standardized for wireless communication standards within 3GPP BMS. Turbo codes. Turbo coding is an iterated soft decoding scheme that combines two or more relatively simple convolutional codes and an interleaver to produce a block code that can perform to within a fraction of a decibel of the Shannon limit. Predating LDPC codes in terms of practical application, they now provide similar performance. One of the earliest commercial applications of turbo coding was the CDMA 2001X digital cellular technology developed by Qualcomm and sold by Verizon Wireless, Sprint, and other carriers. It is also used for the evolution of CDMA 2001X specifically for Internet access. 1X CVDO, like 1X, AVDO was developed by Qualcomm, and is sold by Verizon Wireless, Sprint, and other carriers. Local decoding and testing of codes. Sometimes it is only necessary to decode single bits of the message, or to check whether a given signal is a code word, and do so without looking at the entire signal. This can make sense in a streaming setting, where code words are too large to be classically decoded fast enough and where only a few bits of the message are of interest for now. Also, such codes have become an important tool in computational complexity theory, e.g., for the design of probabilistically checkable proofs. Locally decodable codes are error-correcting codes for which single bits of the message can be probabilistically recovered by only looking at a small number of positions of a code word, even after the code word has been corrupted at some constant fraction of positions. Locally testable codes are error-correcting codes for which it can be checked probabilistically whether a signal is close to a code word by only looking at a small number of positions of the signal. Interleaving. Interleaving is frequently used in digital communication and storage systems to improve the performance of forward error-correcting codes. Many communication channels are not memoryless. Errors typically occur in bursts rather than independently. If the number of errors within a code word exceeds the error-correcting code's capability, it fails to recover the original code word. Interleaving ameliorates this problem by shuffling source symbols across several code words, thereby creating a more uniform distribution of errors. Therefore, interleaving is widely used for burst error correction. The analysis of modern iterated codes, like turbo codes and LDPC codes, typically assumes an independent distribution of errors. Systems using LDPC codes therefore typically employ additional interleaving across the symbols within a code word. For turbo codes, an interleaver is an integral component and its proper design is crucial for good performance. The iterative decoding algorithm works best when there are not short cycles in the factor graph that represents the decoder. The interleaver is chosen to avoid short cycles. Interleaver designs include rectangular interleavers, convolutional interleavers, random interleavers, S-random interleaver. Another possible construction is a contention-free quadratic permutation polynomial. It is used, for example, in the 3GPP long-term evolution mobile telecommunication standard. In multi-carrier communication systems, interleaving across carriers may be employed to provide frequency diversity, e.g., to mitigate frequency selective fading or narrowband interference. Example: transmission without interleaving. Error-free message. RABBBCCCDRF transmission with a burst error. RABBCCC______DF here. Each group of the same letter represents a 4-bit 1-bit error correcting code word. The code word CCCC is altered in 1 bit and can be corrected, but the code word DDDD is altered in 3 bits. So either it cannot be decoded at all or it might be decoded incorrectly. With interleaving. Error-free code words. RABBBCCCDRF interleaved. ABCUF transmission with a burst error. ABCUF______BCDF ABCUF received code words after de-interleaving. AA_RABBBCCCD_EF_FFG_GG in each of the code words AAAA, FFFF, GGGG, only 1 bit is altered. So 1-bit error correcting code will decode everything correctly. Transmission without interleaving. Original transmitted sentence. This is an example of interleaving received sentence with a burst error. This is __________PLOV interleaving the term. An example ends up mostly unintelligible and difficult to correct. With interleaving. Transmitted sentence. This is an example of interleaving. Error-free transmission. tyfafsclv.ira_only.snorton. Received sentence with a burst error. TEP for __________of.ira_only.snorton. Received sentence after de-interleaving. T_isi_ain_amp_van_. No word is completely lost and the missing letters can be recovered with minimal guesswork. Disadvantages of interleaving. Use of interleaving techniques increases total delay. This is because the entire interleaved block must be received before the packets can be decoded. Also, interleavers hide the structure of errors. Without an interleaver, more advanced decoding algorithms can take advantage of the error structure and achieve more reliable communication than a simpler decoder combined with an interleaver. List of error-correcting codes. Encodes. BCH code, which can be designed to correct any arbitrary number of errors per code block. Burger code. Constant weight code. Convolutional code. Expander codes. Group codes. Golay codes, of which the binary Golay code is of practical interest. Gopher code, used in the Michaelis crypto system. Hadamard code. Hagelbarger code. Hamming code. Latin square-based code for non-white noise. Lexicographic code. Long code. Low-density parity check code, also known as Gallagher code, as the archetype for sparse graph codes. LT code, which is a near-optimal rateless erasure-correcting code. M of N codes. Online code, a near-optimal rateless erasure-correcting code. Polar code. Raptor code, a near-optimal rateless erasure-correcting code. Reed-Solomon error correction. Reed-Muller code. Repeat accumulate code. Repetition codes, such as triple modular redundancy. Spinal code, a rateless, nonlinear code based on pseudo-random hash functions. Tornado code, a near-optimal erasure-correcting code, and the precursor to fountain codes. Turbo code. Walsh-Hadamard code.